Hey everyone, welcome to this explainer. Pull up a chair. If you've spent any time at all writing code, you absolutely know the pain of staring blindly at a generic error message, just begging the code to tell you what went wrong. Well, today we're having a bit of a mentorship session. We're going to dive into how modern AI is finally moving beyond just blindly guessing at fixes and actually learning how to dynamically debug your code.
I mean, we've all been there, right? You get a null pointer exception and you spend hours hunting down where that bad data actually came from, especially when it's your own code you wrote at 2 a.m. A lot of developers and frankly a lot of traditional AI coding assistants try to guess the fix based solely on those static error messages. But let me tell you, that is a massive trap. If you're just relying on the crash report, you are essentially flying blind.
So let's break down the core difference here. Think of static code analysis like just reading a recipe. You see the ingredients, you check the syntax, but you don't actually know how the food tastes. Dynamic execution analysis, on the other hand, that's actually tasting the soup as it cooks. You're watching the code as it runs, you're checking the variables, the memory, the flow. And when it comes to AI fixing bugs, getting to actually taste the code changes absolutely everything. All right, Section 1, Catching the Integer Overflow. Let's look at a concrete example using the infamous Math-79 bug from the Defects4J benchmark. This is a classic case where static analysis completely falls flat. Now, what happens when we throw an AI at real-world code? We refactor things, we rename variables. When the code is perfectly clean and canonical, sure, a static AI might guess the integer overflow fix. But when variable names lose their obvious meaning, that static AI gets totally misled by the testing framework's null pointer exception. It literally starts hallucinating random null checks instead of fixing the actual math. It's just guessing based on surface-level text.
But watch what happens when we switch to dynamic analysis. By tracing the actual variable states during execution, we suddenly see this. A sum variable, which is supposed to be adding positive squared numbers together, suddenly flips into a massive negative number. Negative 1.9 billion. This is an immediate, undeniable giveaway of an integer overflow. No guessing required whatsoever. The execution state tells us exactly what the root cause is.
Which brings us to Section 2, Enter Byte Trace and Dynamic Data Collection. How do we actually get this runtime data without manually littering print statements everywhere? Let's look at the ultimate tool for this. Byte Trace is a lightweight, non-intrusive Java instrumentation tool. And the real magic here, the trick to how it collects execution data, is that it captures precise traces without modifying a single line of your actual source code. Instead of changing your code, it instruments the Java bytecode right at class loading time, inserting tiny, invisible probes. It's basically like putting hidden cameras directly into your code's execution environment without touching the source files at all.
So what are we actually capturing with those hidden cameras? During this instrumentation process, Byte Trace seamlessly grabs your variable states, the branch paths taken, the call stacks, and any exception events. It packages all of this up so the AI can literally taste exactly what the code is doing during execution. We get this incredibly precise function-level view of the exact context where things went sideways.
Moving on to Section 3, the iterative repair loop known as DynaFix. Now that we have this amazing dynamic data, what do we actually do with it?
Well, DynaFix is an AI framework that uses this data to form a human-like iterative repair loop. Let's walk through a typical debugging session. Step 1, we execute the failing tests and instrument the code with Byte Trace. Step 2, we prompt the LLM, like GPT-4, with both the buggy code and those rich runtime traces. Step 3, the AI suggests a patch, and we validate it by running the tests again. And here's where it gets incredibly powerful. Step 4, if that patch fails, we don't just ask the AI to blindly guess again. We do a layered refinement, feeding it the new traces from the new failed attempt.
I really want you to remember this piece of senior developer wisdom. The source code can lie to you. The structure, the variable names, the formatting, it can all completely obscure the truth of what the program is actually doing. But the runtime execution, it never lies. Dynamic runtime feedback always reveals the real problem. And this brilliantly illustrates the engine behind DynaFix, the Layered Progressive Repair, or LPR strategy. This is exactly how developers use runtime traces to validate their hypotheses. If a patch compiles but fails the tests, we don't just throw our hands up in frustration. We run it, we get a new execution trace based on that modified code, and we refine our hypothesis. It's a continuous, closed-loop process grounded entirely in concrete runtime behavior.
Section 4, Bulletproof Robustness. Let's shift our focus to how this dynamic feedback creates a literal superpower against tricky syntax changes. See, DynaFix easily survives variable renaming. It completely ignores formatting shifts. Why? Because it focuses purely on execution semantics. Remember that Math 79 bug? It didn't matter what we named the variables, because the execution trace still showed a positive number mathematically flipping to a negative number. The execution semantics remain perfectly stable even when the code's surface changes dramatically. That is a real game changer.
All right, Section 5, the benchmark showdown. GPT-4 versus GPT-4o. Let's look at some hard numbers to see how these underlying models perform when they're supercharged with this dynamic trace data.
This really illustrates the power of dynamic context. GPT-4, when paired with DynaFix, fixed a massive 236 single-function bugs. But what's even more impressive to me is that the faster, much cheaper GPT-4o model still repaired 186 bugs. So even the cheaper model, when given this execution-level dynamic information, absolutely crushes traditional static AI tools. And notice the overlap in this diagram here. By utilizing runtime data, DynaFix isn't just fixing the easy bugs. It actually fixes 23 completely unique, highly complex bugs that every single other baseline tool failed to solve. These are the kinds of bugs where you absolutely need to see the intermediate variable states, like an unparsable string causing a crash deep in a call stack, just to understand what's actually broken. And here's the absolute kicker for anyone worried about API costs. Because we stop relying on blind trial and error, DynaFix cuts token consumption dramatically. On average, it uses about 80,000 tokens per bug, compared to something like 270,000 tokens for traditional agent approaches. That is a 60 to 70% reduction in tokens. It makes this method incredibly cost-efficient. You're getting better fixes, faster, for less money. So, where is all of this heading? The future of this workflow goes way beyond just reading traces. Frameworks are pushing towards active debugging. This means future AI agents won't just observe, they'll actively set breakpoints, step through code, and modify states on the fly. They'll have an unprecedented level of interactive debugging power, essentially operating a command-line debugger entirely autonomously. So, I'll leave you with a provocative thought. The next time you're faced with an impossible bug, are you still going to rely on just reading the recipe and guessing, or are you ready to start tasting the code with dynamic traces? That wraps up our explainer on dynamic debugging in DynaFix. If you found this breakdown helpful, please smash that like button, share it with your fellow developers, and subscribe for more deep dives into the tools shaping the absolute future of software development. See you next time.